Webinar corresponds to part of the lecture on the rhythmical excitation of the heart in the normal ECG. This part will only cover the ECG, how waveforms look the way they do, the normal durations and voltages of various waveforms or segments, and a little bit of discussion on refractory periods in cardiac muscle. When we look at an EKG, otherwise remember is also called an ECG, what you're looking at is not single action potentials. What you're seeing is multiple action potentials that's taking place in the heart at any given time and is recorded from the surface of the body. Remember, the electrodes are the adhesive pads that have this conductive gel that's attached to your skin. The electrodes are then hooked to the monitor or the EKG machine by the wires, which we refer to as leads. When you record the EKG, what you're seeing is kind of summed electrical activity, and what you're going to be observe is we have waveforms. Waveforms are things that you have deflections, say a positive deflection or negative deflections. We have segments, which is areas between waveforms, and we have intervals, which include waveforms and areas where we have no current flowing. So one thing though I want to emphasize is anytime there is current flowing, you will see deflections in the EKG, say an upwards or downwards deflection. These points here, these baseline recording, there is no current flowing. There is no potential difference being measured through the heart. So what we're going to be doing is, first thing is I want to explain to you why things look the way they do. First thing is you have to understand how the EKG is standardized. Pretty much, why do we standardize an EKG? This is so if I run an EKG in Texas, someone in New York or Russia can look at it and still interpret it. I don't have to have my own way of doing an EKG in different areas of the country or the world. The ECG paper is arranged with grids, these horizontal and vertical lines, and it provides a printed record of the cardiac electrical activity. The time and voltage are measured on your graph paper. The standard speed for recording EKG is about 25 millimeters per second. If someone changes that, they must inform the physician or whoever's interpreting it that the chart speed has changed, because that will affect how you standardize the time. Now, if you notice on the horizontal axis, this is measuring time, and each of these little boxes represents a millimeter, and a millimeter corresponds to 0.04 seconds. So for every one of these little boxes, 0.04 seconds has elapsed. You have over here in this box, you notice that we have kind of like darker lines where they're kind of separated into larger squares. Each little tiny square is included in this larger square, and each larger square includes 5 boxes to the horizontal and 5 boxes vertically. The big box would correspond to 5 millimeters because it has 5 boxes, and so a big box from here to here would represent, in the course of time, 0.2 seconds has elapsed. The biggest thing to remember is just really remember that 1 millimeter or one little box represents 0.04 seconds. You can also determine voltage on the EKG, and you need to look at the vertical axis. Again, this is broken up into 1 millimeter boxes. Every little box represents 0.1 millivolts. So if we have a bigger box, you have 5 little boxes that make up a big box. That whole box would represent a total of 0.5 millivolts. it's best to just remember what a small box or a millimeter represents. So in course of time, which you're recording on the x-axis, 0.1 millivolts corresponds to a millimeter, or 1 box. For voltage, you look at the vertical axis. 1 small box is a millimeter, and it corresponds to 0.1 millivolts. And yes, you do have to know that. It's very important that you know those conversions. So for example, why would I want to use this? Well, if you look at, say, the QRS complex right here, tell me how long did the ventricles take to depolarize? So the QRS complex represents depolarization of the ventricles. It begins right here and it ends right here, and this corresponds to 2 boxes, which would be 0.04 times 2, which is 0.08 seconds. So it took 0.08 seconds for the ventricles to depolarize. If we talk about voltage here, what's the voltage of the R wave? R wave peaks here, it comes down here to this baseline. This corresponds to 5, 6, 7, 8, 9 boxes, so that is 0.9 millivolts. Other thing to keep in mind is when we're looking or recording the EKG, we have on the body surface a positive recording electrode and a negative recording electrode. So for example here, this represents maybe if we're running a standard limb lead 1. The positive recording electrode is placed on the left wrist. The negative recording electrode is placed on the right wrist. Well, it so happens, and this is a ECG rule, is if the net electrical current in the heart is moving towards a positive electrode, you will see an upwards deflection. So if this current is flowing towards the positive recording electrode, you will see an upwards deflection. If the electrical current is moving away from that positive recording electrode, if it's moving towards the negative, you will see a downwards deflection. Another thing that you will notice is the magnitude of the waveform. There's a few things that determine magnitude. One of them is that how the average current is running relative to the lead of axis. So if this is your standard limb lead, if the average current flow is going parallel to that lead, you'll get your maximum deflection. As it moves away, it's not moving parallel, as it's moving away from it, the magnitude diminishes. If it's running perpendicular to the lead, you will see a recording that is either baseline or what we call equiphasic. So if I did the math here and determined the algebraic sum of the voltage, these guys, this is a positive, this is a negative voltage, these end up being 0. They cancel each other out. So this is another thing to keep in mind. Whether or not the waveform is upwards or downwards deflected is determined by how the current is running. Is it running towards the positive recording electrode? It's going to be an upwards deflection. If it's moving to the negative recording electrode, it's a downwards deflection. Magnitude is determined by how it's running relative to that lead. Maximum deflection if it's running parallel. As it moves away, if it's running perpendicular, you will have a baseline or an equiphasic recording. Magnitude is also can be influenced by timing. How much time did it take for that particular event to take place? So on an EKG, here the QRS complex represents depolarization of the ventricles. Well, the T wave represents repolarization of the ventricles. Same amount of muscle, but is depolarization quicker than repolarization of the ventricles? Well, depolarization of the ventricles uses that cardiac conduction system, uses that Purkinje system, the Purkinje fibers. It's much quicker to depolarize the ventricles than it is to repolarize. And repolarization of the ventricles does not utilize the cardiac conduction system, so it's slower. So you'll notice this waveform is a little bit wider, and the maximum voltage that you see in the vertical axis isn't as large. But if you measured the amount of, or the area in these curves, they would actually be equal. Now, we had to hand draw these, so it may not be exactly, but the overall voltage or the area under these curves would be the same. But how deflected that these waveforms are, one of the things is determined by timing. Now, one thing I forgot to mention was also magnitude is determined by the amount of muscle mass. The more muscle mass, the greater the deflection. The reason why is the more muscle, the more electrical activity, the larger the voltage that's going to be recorded. So, for example, if you look at the P wave, which represents the depolarization of the atria, versus the QRS complex, which represents depolarization of the ventricles, the voltage recorded from the ventricles is much greater because the ventricles have much more muscle mass than the atria. So that's another thing that can determine magnitude. So magnitude can be determined by the amount of muscle mass, the timing, how much time is required to do that depolarization or repolarization, and how the average current flow is running relative to the lead. Now, one thing that we're going to be showing you is I'm going to show you some examples of some of the waveforms and go over why you see, is it upwards or it's downwards, why the magnitude is the way it is, why is it wide or narrow. But what you're going to see is on the pictures, you're going to see that I've drawn arrows. And these arrows represent vectors, something that you will encounter in other courses, including radiology. Now, vectors are used to demonstrate magnitude and direction. Where the tip of this arrow is, that's the positive end of the vector. The other side is the negative end of the vector. The arrow always points in a positive direction. The size or the length of the vector will determine voltage. The longer the vector, the greater the voltage, and the vector's giving you an idea of direction. It's pointing to the average current flow. So in this picture here, I have this big red arrow, which is representing what we see, the vector that would represent for depolarization of the ventricles. It's very large vector because the ventricles represent a very large muscle mass. And it runs a little bit down and a little bit to your left because that represents the average current flow through the ventricles. Now it's moved a little bit to the left because the left ventricle is a little bit larger than the right ventricle. And so it takes a little bit longer to depolarize the left than it is the right. So if you're looking at averages or average current flow, you're going to spend a little bit more time on average depolarizing to the left, and that's why you see the vector drawn the way it is. Now if we look at some examples, I'm showing you some waveforms as they're depicted in Standard Limley 2. This is the most popular recording to use in textbooks because the Standard Limley 2 gives you the best tracings. They give you the largest wave peaks, so it gives you the prettiest picture. So what we're representing is if I'm running a Standard Limley 2 where the negative recording electrode is off on your right wrist, the positive recording electrode's on your left leg. And so we're looking at the heart going down in this direction. If you notice the P wave, P wave represents depolarization of the atria. The average vector that you're seeing of current flow of the atria is pointing a little bit to the left. The reason why is the right atria depolarizes a little bit before the left atria, because remember, everything starts up here in the SA node, and then the impulse has to go over to the left atria using those interatrial bands. So this is going to depolarize a little bit before the left. So left side taking a little bit longer to depolarize. On average then, the average direction of current flow is going to be moved a little bit to the left. Now because the atria are small, the voltage recorded is not so good. So you see the P waves are not very large waveforms. The arrow is pointed towards the positive recording electrode. That's why it's an upwards deflection. The P wave is rounded. It's not spiked like you'd see with the QRS complex, because the action potentials or the current flow through the atria are slow relative to the ventricles. The ventricles use that Purkinje system, which are a lot quicker, so it's a little bit slower to depolarize the atria than the ventricles. What you'll also notice is, or I want you to think about, is if you accidentally, which has happened in lab, put your positive recording electrode up here and your negative recording electrode down here, what would your P wave look like? And I'd be walking by going, whoa, wait, what's going on? But if you connect your electrodes wrong, your P wave won't be upwards deflected, it would be downwards deflected, because you connected your electrodes wrong. But if you connected your electrodes correctly, and I see a inverted P wave, I may see that in conditions where you have electrical impulse that was generated down here towards the AV node. So if something fired here, the impulse will be moved down through here to the ventricles, but also up in this direction to depolarize the atria. And so that vector is going to be running towards the negative recording electrode, and you'd pick up a inverted P wave. Another waveform to look at. We're going to be looking at your QRS complex. It's composed of three waveforms, a Q, an R, and an S. The Q wave represents depolarization of the interventricular septum. That's the first part of the ventricles to depolarize. The first Purkinje fibers off the bundle branches are the left ones. So the direction of average current flow tends to be a little bit from left to right. So this is, you'll notice the vector is kind of running more towards the negative recording electrode. So Q wave is a downwards deflection. It's always a downwards deflection. What you'll notice is the Q wave is fairly small because it doesn't represent a lot of muscle mass, and the vector is tending to run a little bit more perpendicular. Here's the axis, here's the lead of axis, it's running more perpendicular. So if you were in lab and you didn't see a Q wave, doesn't mean your septum did not depolarize. Is most likely is that your vector, your average current flow in the septum, is running perpendicular to the lead of axis. If I run different views of your heart, do another standard limb leads, I probably want to pick up that Q wave. But it so happened with running a standard limb lead too, depending on your heart, how it's situated in your chest wall, that vector may be running perpendicular to the lead of axis. So the Q wave is not very big because not a lot of muscle mass, plus also the vector is running relatively perpendicular to the lead of axis. The R wave. The R wave is an upwards deflection because the vector, the average current flow through the ventricles, is running towards the positive recording electrode. The R wave represents most of the muscle in the ventricles from apex up to the base, but not including the base. So this involves a lot of muscle mass. That's why the R wave is such a large waveform. A lot more muscle mass. It's also the vector is running pretty close to parallel to the lead of axis, so it's going to be a fairly large waveform. You'll notice that the R wave is a little bit, or quite a bit, usually narrow. With this, we hand drew these, but normally if you look at an EKG, the QRS complex is much more narrow than the P wave because the ventricles depolarize a lot quicker than the atria because of that Purkinje system. Also, let me go back, which you won't see here, we can just draw it in, is the S wave. S wave represents depolarization of the muscle fibers up at the base of the heart. If I had drawn the vector would be kind of running more towards the negative recording electrode. That's why it's a downwards deflection. The S wave is not a very large waveform, not a lot of muscle mass, and the vector is running relatively perpendicular to the lead of axis also. So overall, the QRS complex represents depolarization of the ventricles. You're just seeing different parts of the ventricles depolarizing. Now what I'm going to do right now is kind of go over some of the waveforms, the intervals, and the segments, and go over some key bits of information that I want you to remember. This is very important that you know what is considered normal, because when we go into the abnormal EKG, it will make a lot more sense. So the first thing we're going to do is we're going to be looking on that chart in your notes, which goes over the various waveforms and intervals, and what we're going to be looking at is what we see on a standard Limley 2 EKG. Most of the stuff that I'm going to say is in your notes, but it's going to be very important, if it's not in your notes, that you need to add it. So the first thing we're going to look at is the P wave. The P wave is symmetrical. It should be positive in lead 2. I gave you an example of where it would be negative, such as not hooking up your leads right, or if you had the electrical impulse being generated near the AV node. The P wave shouldn't be more than 2.5 millimeters in height, and that would correspond, you can answer it, what would that correspond to voltage? So you'll need to convert millimeters to voltage, okay, so to millivolts. It shouldn't be more than 0.11 seconds in length. If the P wave is a little higher than normal, it's not symmetrical, or maybe a little bit more prolonged, that can indicate problems with depolarization of the atria. We may see things with some abnormal generation of the impulse, such as the example of an inverted P wave in lead 2, if we had an impulse being generated from near the AV node. You can get changes in the P waves with atrial hypertrophy. But we're not going to do a lot. Pretty much, we're not going to really concentrate on atrial hypertrophy this trimester. It's more ventricular. The PR interval. Now the PR interval represents from the beginning of the P wave to the beginning of the QRS complex. So I've given you two examples here. This is someone that has a Q wave. So beginning of the P to the beginning of the Q wave. If you do not have a Q wave, you need to measure from the beginning of the P wave to the beginning of the R. So that's why we say it's the beginning of the P wave to beginning of the QRS complex. What it represents how much time that the electrical impulse took to go from the SA node, from in the atria, down to the ventricles. The normal time that this should take is anywhere from 0.12 to 0.21 seconds. That's about the amount of time it should take for the impulse to get to the ventricles. If it's abnormal, such as if it's prolonged, it can indicate abnormal conduction through the AV node. So big thing you need to remember is that the PR interval is a good thing to look at if you want to evaluate conduction through the AV node. Disturbances in the AV node will result in an abnormal PR interval, and it will be prolonged. It will be longer than 0.21 seconds. If you have a PR interval greater than 0.21 seconds, they refer to that as a first-degree AV nodal block or first-degree AV junction block. On the lecture on arrhythmias, we'll go over some other things that may that are also called AV nodal blocks, but this is an example of a first-degree AV nodal block. Now the QRS complex. Now the QRS complex represents depolarization through the ventricles. This picture here, which obviously differs from what you have in your notes, and you can draw these in if you need to, is I want you to show you that there's a lot of variation in the QRS complexes. Everybody's may be a little bit different. This is your normal QRS complex or textbook QRS complex, but some of you did not have a Qwave, so it looked like this. You just had an R and an S. Some people don't have an S, so it's just a Q and an R. Some have what we call a QS, so it's like this, just a QS. Some people just have an R. Some people have, say, an R prime, or an S prime. I call this the bunny ears. Now, why the R prime, S prime? I can distinguish what creates or is considered to be an R prime or an S prime. The Q wave is a downwards deflection. The R wave is your first upwards deflection. Once it goes below baseline, it's an S wave. If it goes up above baseline again, that's an R prime. If it goes down below baseline again, that's an S prime. There are times where you may see an R double prime if it goes back above baseline. So this may seem very weird. All of these can be considered perfectly normal as long, this is the important thing to remember, they can be considered perfectly okay as long as the duration is fine. And the duration needs to be 0.06 to 0.09 seconds. If that duration is greater than 0.1 seconds, we have an incomplete block through the ventricles. There's been a slowing of conduction through the ventricles. If it's greater than 0.12 seconds, they refer to that as a complete block. What the QRS complex gives you information-wise, one of the things it can evaluate is how conduction was through the bundle branches in the Purkinje system. Since the ventricles utilize the Purkinje system, if this is prolonged, it may tell you that we may have a block in conduction through the Purkinje system. So that's an important thing to remember. So you need to remember that what the normal duration is. If it's longer than normal, somehow we've got a delay in conduction through the ventricles. One of the things that could cause it is a problem with the bundle branches or the Purkinje system. Now, following the QRS complex, the very end of the QRS complex, we have what we refer to as the J point. This is the point at which the QRS complex returns to baseline. The J point is a very important landmark for all of us. The J point is always zero potential. It's always a point where no current is flowing. So even if we've got something wrong, like for example, injury in the myocardium, which we'll be showing you, we may have some abnormal current flowing through the heart, this point always, there will never be current flowing, ever. This represents when the ventricles have completely depolarized. There's no net potential or net difference or potential difference being measured. So this will always be baseline. What we're going to use this for is as a reference point for looking at something called the ST segment and the TP segment. Now, what you see right here is what we call the ST segment. It's from the end of the S to beginning of the T wave. That segment should be isoelectric or zero potential, like the J point, but you're allowed a little bit of variance. This may be up here or down here. You're allowed a millimeter variance above or below, which corresponds to 0.1 millivolts, a positive 0.1 millivolts if it's up here, or down to minus 0.1 millivolts. That's considered to be perfectly fine. That's normal variance. But if it's more than that, there's something wrong. So this again is representing the ST segment. If it's deflected, or if you see this more than a millimeter above or below where the J point is, it can indicate ischemia, infarction, injury in the heart, or things like pericarditis, which is inflammation of the pericardium. So that you should not have that ST segment be more than a millimeter above or below the J point. If it's above the J point, they refer to it as an elevation, an ST segment elevation. If it's below, they call it a ST segment depression. The TP segment is another waveform, it's really a segment, another area on the EKG which should be isoelectric. There should be no current flowing, and so you should not see any deflections. It represents from the end of the T wave to beginning of the P wave. Now this is it's just like we talked about with the ST segment. It should be isoelectric, but you're allowed a little variance. It could be a millimeter above from what you compare to the J point, or a millimeter below, which again corresponds to 0.1 millivolts above or below the J point. If it's deflected more than that, or if it's elevated or depressed, there is something wrong. Again, same thing, examples when I told you about the ST segment. Ischemia, injury, infarction, pericarditis. When we look at those conditions, specifically ischemia, injury, and infarction, we will be looking at pretty much looking at the TP segment relative to the J point. And there's going to be a reason why, but both the ST segment and the TP segment are allowed only a millimeter above or below from what the J point is. If it's more than that, it's abnormal. The T wave. Now the T wave represents repolarization of the ventricles. It's usually a little bit asymmetrical. Of course, we hand drew these, so this actually kind of looks symmetrical, but it's usually asymmetrical. In most leads, it will be positive in most leads, but you may see it be inverted in lead 3, so don't be concerned if you see it inverted in lead 3, and in your chest lead, V1 chest lead, it may be inverted, so don't be concerned if you see it inverted in those leads. If you start seeing it inverted, say in standard limb lead 2, that's considered a T wave abnormality, and it can be indicative of various conditions. Now the voltage of the T wave should not be more than 5 or 0.5 millivolts, or if you measured it, it shouldn't be more than 5 boxes in height. So it should not exceed 5 millimeters in height, or corresponding to 0.5 millivolts. Examples of things that can cause or result in what we call T wave abnormalities. You may see an inverted T wave in myocardial ischemia. You may have a inverted T wave in digitalis toxicity. So digitalis is a drug given to heart patients, and if they get too much digitalis, it can create changes in the EKG. So often, people on digitalis therapy are monitored with the EKG to make sure they're not getting too much of it. It can cause an inverted T wave or what we call a biphasic T wave. So the first part, let me see if you can see, just kind of watch the cursor. It will go up and down and back up, and then you average these two together and they end up being overall voltage of 0, like I had mentioned earlier in the lecture. Another thing that can result in abnormalities of the T wave, you can get tall peak T waves, where that T wave starts to become very narrow and very tall with hyperkalemia. You can also get a flattened T wave with a larger U wave in hypokalemia. So things that can affect the T wave would be things that maybe affect conduction, or I should say the things affect how long it took to repolarize the ventricles. That can do it. Other things that are associated with inverted T waves would be left ventricular hypertrophy and even left bundle branch block. So those things that you may see inverted T waves. The idea, or this is something, it's very confusing for a lot of students, and I don't blame you, is some of you may have already asked the question, why is the T wave upright? Why is it not downwards deflection normally? Well, the T wave does not follow the rules that we said with if a wave or average current flowing is running towards a positive recording electrode, it is an upwards deflection. Here, I should have said that it's really the wave of depolarization is running towards the positive recording electrode. It's an upwards deflection. The rules of repolarization are different. Now, generally, normally, repolarization of the muscle fibers always start at the muscle fibers out near the epicardium and go to the endocardium. And that seems kind of odd, because when you depolarize the muscle fibers from the endocardium out to the epicardium. So you would think the first to depolarize should be the first to repolarize, and no, that's not true. The refractory period of those muscle fibers near the endocardium is a little bit longer, and so you always depolarize from endocardium to epicardium. You repolarize from epicardium to endocardium. And so if that's what we see, that's what's going on, your T wave will be upright. However, for example, something like severe hypertrophy. If something is taking way too long to depolarize, because you've got a lot more muscle mass, the fibers that were near the endocardium that may have been, I've already depolarized you, and I'm still waiting to depolarize some muscle fibers way down the line, they can come out of its refractory period and then repolarize first. And so what happens is the T wave will then be inverted. It seems very complicated, but just as long as you remember that the repolarization of a T wave, or the waveform you see, is usually upright. Things that really severely delay repolarization or even depolarization, that you can end up with inverted T waves. So here, these are examples of some T wave abnormalities. So here's your hyperkalemia. Here's what you may see in ischemia. And in ischemia, the T wave will usually look symmetrical. In something like a bundle branch block or hypertrophy, the inverted T wave won't be symmetrical. And here is the example of hypokalemia. Another thing to look at on the EKG is what we call the QT interval. QT interval corresponds to the beginning of the Q to the end of the T. This represents or includes your depolarization of the ventricles and repolarization of the ventricles. In your notes, it says time period of ventricular contraction. It's not quite exactly right because the ventricles really don't contract to the beginning of the R wave, but it's pretty close. The QT interval varies. The length of it will vary depending upon something like your heart rate. QT interval, though, also may be shortened in something like hypercalcemia. It can be longer in hypocalcemia. There's other things that may affect the QT interval, but it's beyond our scope. The U wave, or that wave of unknown origin, you saw that when I showed you hypokalemia. But some people, we see this in, and it may not be anything indicating that anything's necessarily really wrong. Usually, if you start seeing a U wave, it may indicate that some area of the ventricle is repolarizing a little bit later or maybe a little bit slower than normal. So don't always think if you see a U wave there's something terribly wrong with this person. You need to look at the entire picture. Now the last thing I want to mention are refractory periods. So earlier in the try you learned about what a refractory period was. A refractory period is indicated by a time where if you stimulate that muscle again, you will not get a response. And there's a difference between an absolute and a relative refractory period. With cardiac muscle, the absolute refractory period corresponds to the beginning of the QRS complex to the beginning of the T wave. This represents the time where if you send an impulse or generate an impulse to that muscle, you will not get a response. Okay, I don't care how strong the impulse is, you will not get a response. You cannot stimulate that muscle again. The relative refractory period corresponds in cardiac muscle, beginning of the T wave to about 3/4 of the way into the T wave. This represents a time where you may be able to stimulate that muscle again, but that stimulus must be much stronger than normal. So here you can generate an impulse that's much stronger than normal, and you may be able to get the heart to depolarize again and contract again. The refractory periods, though, overall, when you look at cardiac muscle versus skeletal muscle, cardiac muscle's refractory period is much longer than skeletal muscle. What's the significance? Cardiac muscle, you cannot get tetany, because tetanized cardiac muscle will not be an effective pump. It's protective. So the refractory periods in cardiac muscle overall are longer. Refractory periods, though, differ between atrial and ventricular muscle. Because the refractory period in atrial muscle is less than the ventricles, you can get faster rates in the atria. So if there's an example where you have some little disconnect where the atria are beating a little bit different than the ventricles, the atria can beat at a much greater rate than the ventricles. You may see this in something called atrial flutter.